Hello, my name is Alexander Shalimov. I'm faculty at Moscow State University and researcher at Applied Research Center for Computer Networks. My co-author Pavel, he did the main job, implementation job. He is a programmer and and recently joined Moscow State University as first year PhD student. Oh. We would like to present you an interesting approach of how you can speed on your networking application on top of your OpenFlow controller. First of all, I would like to ask a question: what is the ideal controller? Mostly what we want from the controller. We want it should have a lot of functionality in order we can use it from the box without any modifications on any networks. On any topology, in any infrastructure. Also, it should have a nice programming interface if you want to create your own applications. The most important question is performance. It should be fast. And performance, I mean throughput, events per second. For example, in the modern data centers, generates at least 20 million events per second, and you should process all of them. Also, as fast controller we have, as more reactive and responsive it can be. So you can ask your network more deeply about topology more often, about send testing packets, make your measurement more often. And so the last one is it should be reliable and stable, so it should work without any problems for a long period of time. And the question, do we have such ideal controller? The short answer, not yet. Some controllers have very good programmable and a lot of functionality, but the performance reliability is very bad. Someone has a good performance, but reliability very bad because, for example, we send the malformed packet and it just crashes. What about our controller? The first version of our controller. It's fast and reliable, but the programmability issues is not very good. Let's discuss this. On March, in Open Networking Summit, we presented our high-performance controller. We implemented it as a model in Linux kernel. It's very fast. It's 6 times faster than the existing beacon controller. It's super fast because in the kernel you don't have context switching on network communications. Also, you don't use very advanced memory translation mechanisms that we have in user space. In the kernel space, it's much more easy. But what problem we have? It's very hard to develop your own program. It's low-level language. It's very low-level C without any very famous and most important well-used libraries and tools. Moreover, it's very easy to crash your system. If you made very little mistake, your whole system will crash. And this is a problem. And our goal was how we can increase the programmability of our controller. Let's start from the controller itself. The controller can be divided into 3 parts. The first one is the networking part. It communicates with switching devices. It also consists of some functionalities that are encoded in your controller. That the most frequently used functionality, for example, topology discovery and point tracking and so on. And on top of that, you have your applications. This is structure true for all controllers. Almost all existing controller is implemented in the user space, as we talked. And we have our controller implemented in the kernel space. On the left side, we have a lot of applications, but very bad performance. On the right side, we have very high performance, but almost no application. It's very hard to develop. And the question, what is in the middle? And this, we introduced our approach that we call offload architecture. We in the kernel you have very time-consuming and frequently used code. For example, it's communication with your networking devices. It's very well-used services. For example, topology discovery. It doesn't make sense to run it in the user space. It's the controller itself should reconstruct, reinvent your topology. And in the application side, applications run in the user space. You can use your own functionality, your own libraries that you want. It's very easy. You have nice debugging tools and so on. But we need a very nice and well-defined communication interface between user side and the kernel side. And together with this approach, we can achieve very nice performance together with a lot of functionalities that we can get from the user space controller, from the user space side. Here we have some implementation details of our architecture about how we communicate between the user side and the kernel side. On the kernel side, we have several kernel threads, and the user side and the application side, you should have the same number of threads. Threads connected with dedicated threads through the shared memory. There are two types of shared data structures. The first one is the queues. We have control queues and data queues. Control queues, we send the commands if you would like to add something from the kernel side. For example, what is the topology? Data queues are used to sending, for example, packeting messages from the kernel side to user side. But in order to speed on this stuff, we send through data queues, not zero OpenFlow messages. We use preparsed OpenFlow messages. This is why we get some performance. So in the data queues, you have preparsed data structure. So you have a type, for example, packeting messages. You have preparsed info. And this means that you don't need to parse in the user space the packeting messages from the scratch. And also you have pointer to the buffer where the original packeting messages reside. What else? As I already told, in order to get the high performance and to avoid locking, we assume that the application threads should have the same number of the user space should have the same number of threads as the kernel, in kernel. Because if you have the less number of threads, you didn't get right performance. If you have the much more number of threads, you need some locking mechanism in order to access the queues. What else? Why we think that we can offload something to the kernel space? When we did measurement, we understand that while user space threads is 100% loaded, the dedicated kernel space is only 25% loaded. This means that the rest 75% we can use for topology discovery, for example, for any services and functionality. All access to the services can be done from bars data queues if you would like to receive pushing messages, push notification, or you can ask from the control messages for the topology, for example. The current we support topology discovery, and we had some work on endpoint tracking, so we try to understand where is the current endpoint resides. About programming interface. From the programming side, the controller looks like special devices that you can open through the, for example, C program. So you should open dev control. You should subscribe to events through EOCTL command. Access to shared memory using kernel infrastructure. And that's it for starting applications. The rest is the main loop that you can cite on the right side of the slide. You directly call the poll commands that you ask from the kernel controller for the events. If there is any data events or control events. Here is the slide. In the cycle, you receive reading how many packets you have in the kernel side. retroactively read all packets from the data queues, process in L2 learning functions, and at the end you call a write command in order to flush out buffers with offload mode commands. And that's it. What about performance? If you compare it the input-output throughput, that's traditional test using CBH into L2 learning applications, we get 2.5 faster than Beacon, for example, the fastest controller Beacon. But of course it's less than just in-kernel controller that resides in the whole in the user space. As for response time, is 50 microseconds. For services times, usually for topology discovery and for path calculation, it's in the kernel space, it's 4 times faster than in user space, running in the user space. And that's it. We introduce an interesting approach how we can speed run the applications. The most benefit you can get if you resize the most time-consuming and frequently used functionality in the kernel space. It allows you easily to create high-performance application and use our kernel-side controller. And mostly, hopefully, with this modification, our controller can be ideal. So we have very nice. So for now, you can easily create your own applications. That's it. Questions? The functionality. Some part of our controller is available on our GitHub. It's called our controller called Runas, the Russian network operating system. The user space size for now is in controller. It's the first version. By the end of the year, we upload the rest of functionality. Thank you.
Thank you for presentation. I want to ask a question. What's the difference between the service and the application? I see the NFV in the service, but how about the extension or other applications? Thank
you. I didn't get the question. Are you asking about hardware appliances or what?
The difference between application and the service.
Okay. The difference is the services in our terminology is very frequently used functionalities provided from the controller. For example, it's what we call northbound API. For example, from the applications, for example, a lot of applications that people can write need topology or path calculations, right? So this is we call the service because like a library for the comparing for traditional languages, programming languages. So it's just frequently used functionality.
At this slide is comparison of controllers. You say about performance and reliability of controllers. How you estimate reliability of controllers?
This was done in our research mostly 2 years ago. We measure reliability by setting malformed OpenFlow. There are 2 tests. First one, we set malformed OpenFlow messages to the controller and see what happens. For example, we change the type of the messages. So we say that it's a packeting message, but inside we have feature reply body of payload. And the second one test was we run the controller for the long period of time and see what happens.
Could you please explain how do you handle controller errors? From my understanding, it's very crucial to handle kernel errors in such applications.
You mean if someone writes a bad application in the kernel side? This was the main problem. We understand that only we can write new application for our controllers, because it's very hard to learn other people to write some applications. This is mostly people. So even we, sometimes when we find the bug, our system might crash several times when we understand what happened. This is why we try to create a nice programming interface from user side. This is our work.
So thank you very much, Alexander.